Welcome to a lesson with Dr. Powell. Let's take a look at a result of Yoneda's lemma and how we can use it to talk about two functors being what we call adjoint to each other. This is kind of nice because you kind of turn one thing into something else, and you can pull results in one category to another category very nicely using adjoint functors. We'll see some examples of that in another video. But for now, let's kind of think about the setup. So from Yoneda's lemma, we know that natural transformations from a Hom functor like HA right here, this is input right here, and a functor, any functor here, well, this functor right here is actually kind of a composition of two functors, a Hom functor and a G functor. And it actually starts in the category C, just like this starts in the category C. So they both start from the same category, both landing in sets. And we know that we have any natural transformation between two such functors is given uniquely by an element of this, the output of this functor when we plug in A. Now, what if we actually had a functor? Let's just assume, what if we had a functor f, which where the output of x right here, so given this functor right here, the output of x was actually A. So f of x is equal to A. So we can actually think about that. Now, if we did have a functor like that, and we had it in such a way that we had a natural isomorphism, not just transformation, but a natural isomorphism between the two functors when we had f of x up here and x down here. And it was even natural in both components. So not only just if the functor is defined over here, but even if it was defined with input over here, then the two functors f and g will be considered adjoint to each other. F will be considered left adjoint and G right adjoint to the other, respectively. Okay, so let's take a look at what we get from Yoneda's lemma even. Now, we actually have that any element in here that determines the natural isomorphism actually comes from the identity up here. And if we have, and the map over here actually determines something in here, it determines the map that goes this way. And we have this nice commutativity. So this also comes from the same map, really comes from this guy over here. Okay, well, this is just, so remember we have a composition of two functors. That's what this functor is down here. So it really follows suit in what Yoneda's lemma is saying. Now, specifically, actually this one diagram, assuming that we have this naturality, we have a natural isomorphism and all that, actually gives us a nice universal type property. Namely, if we given this, which means we have given our natural isomorphism, so saying an element here tells us that we have a natural isomorphism, tells us which one, and then given an element here, well, we could just pull it back up here. So we have something there definitely. So there exists something we can pull it back to, such that we can use it as a map over here, get commutativity, and make this diagram commute. Now, if this diagram commutes, then that means specifically right here, we have this relationship holding. The element in here, f, is given by extending this map, a to x, by a biomorphism g of gamma, because that's what how this map between Homs works, by extension. So we actually get that this element is equal to this guy composed with a to x. Remember where gamma came from. It came from up here. So, well, we can even write that in the diagram. We think of this a to x as being what's called an initial morphism, because things kind of come from it like this. So given a to x and given f, there exists a unique gamma such that g of gamma makes this diagram right here commute, kind of a nice universal property. Now, natural in both components, we actually get a similar version, even thinking about Yoneda's lemma kind of in the other, on the other component. We get identity element here, and we get a unique thing here, which determines the natural isomorphism. Now, because it's natural in both components, actually, this natural isomorphism is the same natural isomorphism that we had in the other component. Kind of fun, but they're both one and the same. So, and actually, we get duly similar universal property, which right here, this is it goes to a morphism here, epsilon y, which we could call it a terminal morphism, even kind of following the same basic idea. Now, using the same basic idea here, let's see how eta x and epsilon f of y are related. Well, because we have this relationship with identity, and we have a map here going here, and we have identity over here, we can look at this diagram, which comes from this natural isomorphism being natural in both components, and we get commutativity of this diagram. The commutativity of this diagram guarantees this statement here, which if you look at this diagram long enough, it'll make sense to you. I invite you to do that. This right here gives rise to something called the unit and co-unit equations, where eta, let's just call that, it's a natural transformation, or it's a map. It can be considered, but I didn't show that in this video. But think of eta as being simply eta x as being that map that we were talking about, but notice it works for every single x. And it really ends up giving a map. If you look at it, let's go back there and actually see what's happening. Notice how it gives a map between x and g f of x. Actually, this map ends up being natural. So eta actually ends up being a natural transformation between the identity functor in the category where x lives and the composed functor gf. Kind of fun. Okay, so we get that eta x is that so eta ends up being an identity functor, and not an identity functor, ends up being a functor between a natural transformation between an identity functor and the composed functor gf, and epsilon is similarly defined to be a natural transformation as well. And we end up getting these relationships where we get the identity transformation between the functor f and f, the identity transformation between the functor g and g. These are kind of two fun equations. I invite you to look at that diagram and again, and think about how those equations work, how we get this popping out of it. Maybe look at the other one that I didn't illustrate. And thank you so much for watching.